Can you hear me now?
Hello?
Hello, can you hear me now?
Yes.
Oh, great. Great. Can you see the screen as well? Share it. So good afternoon, students. In today's lecture, we're going to have a brief introduction of numerical methods and statistical methods. I'm Tony Setumba. I'm a lecturer there at Soroti University. So I'll start by giving you a brief background about numerical methods and statistical methods. And then I'll give you the course outline.
Dr. Setumba.
Yes.
Abigail here.
Okay.
Would you like to unmute the video so the students can see you for a bit? You've been away from them for long.
Ah. Okay. Let me see.
I think that's important.
Let me see if it's possible here.
If you're in position, if not, no problem. But I think it would be good if they had seen you.
Okay, no worries. Let me try to see my camera.
And I think you are able to see them as well in the class. The camera in the class is turned on.
Yeah, I can see them.
Okay.
Maybe we can do this in the next class.
Okay, no problem.
Right?
Yeah, sure.
Okay.
All right, go ahead.
So I'll start by giving a brief outline of the course that we are going to follow. So we're going to look at the part of we shall look at numerical methods. What's happening with my pen?
Emmanuel, is it your whiteboard which is on?
It's mine.
It's yours, okay.
Yeah. Oh. Okay, it's fine now. So we're going to first look at a part of numerical methods. And under this, we're going to look at one. Before we look at the numerical methods, we're going to look at analytical techniques that are going to help us. And under this, we're going to look at first order ordinary differential equations. Then we shall look at linear second order differential equations. And then we shall look at numerical methods. To solve these equations, okay? Under this, we shall look at the Euler's methods. Then we shall look at finite element methods. And then we shall go on to look at differentiation, and particular numerical differentiation, and finding roots of equations. So we shall find solvers of roots of equations. And under this, under roots of equations, we're going to look at one. We shall look at the bisection method. Okay. Then we shall go on to look at Newton's Raphson method. Okay. Method, which is sometimes abbreviated as an NRM. Okay. Then we're going to look at the second method. Okay. Call it the second method. And then we can look at the Broyden's method. Then we can look at the conjugate gradient. Method, okay? But what you should know is that I know you've looked at this, you've looked at the Newton-Raphson method before in high school. And this method only works if you have a function of one variable, but we shall extend it to cases where we have two variables, two or more variables, because most engineering problems have more than one variable. It's hard for you to design a problem that is just in one dimension. For example, if you look at waves, okay? Waves, you have a component in time, you have a component in space. So most of the engineering problems we deal with do not have only one dimension. So we should be able to extend these methods to more than 2 dimensions. Okay? But one of the major things that you should know about these numerical methods of finding roots of equations is that they're local methods. Okay? Maybe you could write down this. Are you noting down what we are studying? So I've said that all these numerical methods are local methods. And what I mean by local methods is that they're based on the Taylor series approximations, based on Taylor series approximations. Okay? And because they are based on the Taylor series approximations, first, they are slow. Okay? And secondly, they all assume that you should have an initial guess or an initial guess or root. Okay? And what does this root say? This root, this initial root or initial approximation should be close to the solution. Okay? Which may not be the case. And why do I exactly say that they are local methods? For example, look at a function like this. Assuming you have a function that is given like this. Okay. So if this is our function fx, and this is x, and this is fx, okay, the axis. So you can clearly say that if I ask you to get the maximum and the minimum of this function, you'll find that you're going to have a minimum here. Let me change the ink. You're going to have a minimum at this point. You're going to have a maximum at this point. You're going to have a minimum at this point, a maximum at this point, a maximum at this point, a minimum here, and this. Okay? So if you have a problem to find the minimizer of such a function, then this method ceases to matter. Reason being, we have so many local minima and local maxima. What I mean by local minima is that you can see this is a minimum, this is a minimum, this is a minimum. and this is a minima, and this is a minima. Sorry, you have a minimum here, right? So if you need to find the minimizer of this function, you're going to find that you have infinite number of minima. And the lowest point, we call it the global minima. It is the global minimizer of the function. Okay? And all these others, we call them local minima. Okay? So usually these methods or techniques are helpful for you to find local minima. But if you need to find a global minimizer of a function or an engineering problem, you may need to approach it in a meta-heuristic approach. Meta-heuristic, I mean more complex, okay? You may not be able to model it with a mathematical expression. And then the other thing, they are local methods because they are all based on the Taylor series approximation. They dictate that you should have an initial solution to the function. Okay? And are you taking notes as we are studying? So if you need to ask questions, you should ask as we are studying. And then feel free to interrupt if you need to see the previous material. You can also ask for it here. And then the video will be available after the lecture. Okay. So we need to go on. Okay. Under the analytical methods, the first order ODEs, we're going to look at first what we mean by an ordinary differential equation. Okay? By ordinary differential equation, we mean an equation that has one or more derivatives. Okay? Of an independent variable. Okay. For example, or you can say dy dx may be equal to some function. Okay. Let me say x, y. This is an ordinary differential equation. Okay. So, and it is dependent on x. Okay. So this is an ODE. And under this, we're going to look at the order of a differential equation. Then we shall go on to look at solutions of ODEs, okay? Because we know that most engineering problems are modeled by differential equations. For example, you could look at electric circuits, okay? Electric circuits, the charges, the currents, okay, that are run within the circuit. They all follow DEs. For example, you can have something like L I bar plus L plus I maybe equal to 0, okay? So I is the current, L is the inductance, okay? So this is a DE, and we could also denote DEs with either this, which implies that this is the same as DI, maybe DT or DX, depending, okay? And then you can denote it with I with a dot. All these denote DEs. All this, okay? These are the same things if you see them. And then we're going to look at separable ODEs, okay? Then we shall look at DEs that can be made separable when they're in their initial stages are not separable, okay? Then we shall go on to look at exact ordinary differential equations, okay? And we shall go on to look at the condition for exactness, okay? And then we are going to look at, is there somebody with a question here? We request you to please send us the lecture slides. Okay, I will share the slides and the video will be shared as well. So we shall look at the condition for exactness. Then we shall look at integrating factors. Okay. And then we shall go on to look at linear first order differential equations. Then under this, we shall look at the method of variation of parameters. Okay. And finally, we shall end our exposition for first order differential equations by looking at applications to an electronics or an electrical engineer. Okay. And under this, we shall look at electric circuit applications. Okay. And then we're going to go on to look at second order differential equations. And under this, we're going to look at homogeneous linear equations. of second order. Okay. Then we shall go on to look at solutions of second order ODEs with constant coefficients. Okay. And then we're going to look at the initial value problems. And also under this first order ODEs, we need to look at initial value problems, okay? IVPs. And then we're going to look at IVPs. Then we shall go on to look at roots and solutions of second order ODEs. Okay. Then we're going to go on to look at stuff like Cauchy's equation. Then we shall look at existence and uniqueness of solutions. Okay. And then we shall look at the method of undetermined coefficients. Okay. And so on. So this will mark the end of analytical techniques. Why should we learn about analytical techniques in our exposition of numerical methods? This is because if you can solve a problem analytically, then we need to revise means of introducing numerical techniques or methods that we can use on a computer to solve and compare our analytical result and the numerical result. And depending on the discrepancies, then we can be able to detect the error in the method that we are using. Okay? And this will lead us to error analysis. Okay? We have looked at analytical methods of solving differential equations, specifically the first order and the second order differential equations at this level. But as you go on in engineering, you're going to look at higher order differential equations, and you will look at methods that can solve higher order differential equations that are higher than the second order and the first order, okay? And under that, you look at interesting stuff like the power series methods, the Bessel functions and Frobenius methods, and so on, the gamma functions, the beta functions, and all that, okay? Then we look at Laplace methods, Fourier methods, and all that, okay? But that is out of the scope of this course. So under this, we need to look at random errors, okay? Then we need to look at approximations. Okay? Under this, you look at both approximations and error analysis. Okay, the two go hand in hand. Okay, Then we shall look at round-off and truncation errors. Okay? And you will look at maximum and minima of a function. Okay? And under this, still numerical solutions. Okay? You remember, if you have something like this, okay? Or you have something here. Okay, if you have this function here, and they ask you to get the maximum or minimum, remember, when you have something like this is a maximum. Okay, if you have something like this is a minimum. But what if you have a situation, you have a function like this? So it's hard for you to say that this is either a max or a minima. And back then in high school, you could call this the inflection point. The inflection point or point of inflex. And when we go to advanced stuff, we call this the saddle point. Okay, so we shall look at minimizers and maximizers because solutions to numerical problems require us to get solutions to functions, to DEs. So we need to look at how we can minimize stuff like minimize fx given a number of conditions or constraints. Okay, they give you constraints. So we need to look at problems like this in numerical analysis. All right. And after that, we're going to look at numerical integration. And under this, we shall look at specifically the trapezoidal rule. And then we shall go on to look at the Simpson's rule. In your high school, you looked at this. But now we need to look at the Simpson's rule. Okay? And we see, or we can strike a performance comparison between the two approaches. Okay? And then we're going to go on to look at if you have maybe certain data, they have given you a task to carry out an experiment to determine the electronic waste in Uganda or in the Teso sub-region, okay? You have your data, okay? You have your data, you have computers, you have monitors, okay? You have the peripherals, you have keyboards, okay? You have the mouse, you have phones, and you need to determine the amount maybe of electronic waste that will be in the Teso sub-region in the next 5 years. Okay. So how are you going to determine where this data lies? Which distribution does it follow? Okay. We call this data fitting. We need to do analysis on particular data collected from an experiment. Maybe we need to determine the particular probability distribution it's going to follow. Maybe we're going to determine the impact of what this information is actually going to cause. So we need a way of studying this numerically. And under this, we shall look at what we call the least squares approaches of approximating functions, okay? So we shall look at the least squares methods, okay, of data fitting, okay? And then we shall go on to look at conditional numbers, and then we're going to look at vector and matrix norms. Okay. Then when time allows, we shall go to the statistical approaches, to more statistical approaches. Okay. But this is not your worry, because we have a course in second year that is probability and statistics. So this material, we could cover it in this particular course. Okay. So let's start today's lecture. So is there anybody with a question? If you have a question, please ask. I didn't write my email. Okay. So if you need to contact me, I run university business on email, and you can get me on any of these emails. Okay. This is more preferred. But if you fail to get me there, you can copy, or if you send on that, you can copy on. This has a single T, this has a double T, and it's a Gmail, this is a Sun email. So you can contact me through that, okay? If you have more urgent information, the email is preferred. Okay, you need reference material for the book, for the course. There are so many reference book, but one, you can look at advanced engineering mathematics. by Krzyzek. Okay. By Krzyzek. Then 2, you can look at advanced engineering mathematics by Stroud. And 3, you could look at numerical analysis. Okay. You could look at elementary numerical analysis, okay, by S.D. Conte and Carl Bo. Then you could look at an introduction to statistical methods and data analysis. Okay. And this is by R. Lehman and T. Longnecker. Okay. So I can share the soft copies of these books. And then one thing, this course is going to introduce you to MATLAB, which is Matrix Laboratory. So I need you to check with the second year students. If at all we don't have MATLAB installations on the computer labs, second year students can help you to get MATLAB. Okay, get MATLAB on your laptops because you're going to be doing some kind of MATLAB programming. Okay, usually in engineering and mostly electronics, electrical, all sorts of engineering, we find MATLAB easy because it is fundamental in solving numerical problems. Okay, so in our exposition, we're going to look at and get some working basics of MATLAB. Okay, so those are the first few things I wanted to communicate before we go into details of the lecture. And let's start the lecture, please. Okay, but feel free to interrupt. So differential equations are fundamental importance, okay, are fundamental importance in engineering because I said many physical quantities and laws and relations are mathematical, okay, and they are in forms of differential equations or they are modeled using probabilistic approaches or stochastic approaches, okay. So that's why we need a proper understanding of differential equations. And secondly, we're going to consider various problems that lead to differential equations, and then we shall explain the most relevant methods to solve them. And usually differential equations are more convenient for computers to solve numerically, okay, because the computer interprets ones and zeros. So if we have our problem and we need to solve it, because some problems are so complex to be solved analytically. Moreover, some differential equations are not linear, okay? So it would be absolutely impossible for you to solve it using hands or what you call your analytical methods and approaches. You may not be able to determine the closed form expression of a particular DE, but a computer can solve it, okay? Or we could use numerical methods. Numerical methods use approximations to solve differential equations, okay? So we're going to look at numerical methods that can be used to solve first order ODEs, okay, and second order ODEs, okay, using finite element approaches. So what do we mean by an ordinary differential equation? This just refers to a relation which involves one or several derivatives of an unspecified function y of x, okay? This relation may also involve the function y itself, given function of x, and it could also include other constants. And examples include one, the equation given in 1, and the equation given in 2, and the equation given in 3. Okay, so all these are ordinary differential equations because they involve derivatives of y, okay, with respect to x. Okay, they can involve even y itself, as you can see here, and they can involve other functions. Okay, so, and we usually use the term ordinary to distinguish the equation from a partial differential equation. Okay, partial differential equations take the form of equation 4. This is how we write partial. Okay, and an ODE is said to be of order n if the nth derivative of y with respect to x is the highest derivative of y in that function. Okay, and this brings the notion of order of a differential equation. Okay, and this leads to useful classifications into equations of first order, second order, third order, and higher order, name it. Okay, so for example, if you look at this function, okay, this is a first order ODE because it is the first derivative. Y bar is the same as dy dx, but if you have d squared y dx squared, then the highest order derivative is 2. Okay, the highest order is 2. So this becomes a second order ODE. And if you go on to the third derivative, then you have a third order ODE. Okay, so we can say that a function 5 y equal to gx is a solution of a first order differential equation on some interval, say a up to b. Okay, and perhaps this interval should be infinite. Okay, or it can be finite. So if the function dx is defined and differentiable, last semester I think you did something in calculus. Okay, so throughout that interval, then the equation becomes unidentity when y and y dash are replaced by g and g bar. Okay, for example, equation 6 is a solution to the ODE y bar equal to 2y. You know why? We could take an example here. Okay. We could take an example. We've said that we have y equal to g of x, okay? And we've said that this is equal to e power 2x, okay, and is a solution of y dash equal to 2y, okay? Can we get g bar? G bar is going to be equal to 2e power 2x, okay? And when we insert or substitute g bar and g, what is going to happen? We're going to see that g bar, which is 2 here, 2 e power 2x, which is going to be inserted here, is going to be equal to 2y, which is e power 2x. And you see the two are equal, okay? And what you need to know is that sometimes a solution of a DE will appear in this form, okay? And we call this implicit form, okay? And you may not be able to express the solution explicitly. So the explicit form is x squared plus y squared may be minus 1 equal to 0. This form is explicit. You can distinguish the terms in x, y, and all that. But sometimes you may not be able to do this, okay? And the solution may take on an implicit form. So you need to note this. In high school, you used to solve stuff and you could express almost everything. But more DEs won't have explicit forms or solutions, okay? And then the other thing, you should note that what if you have a problem, okay, of y bar equal to cos x? You and me will agree that y equal to sine x, y equal to sine x plus 3, y equal to sine x minus 4 over 5. All these can be solutions. All these can be potential solutions to this ODE. You know why? Because y dash is the same as dy dx, simply say. So dy dx equal to cos x dx. When you take the integral, it implies that y equal to sine x plus a certain constant c. So when the constant c is 0, we have this. When the constant c is positive 3, we have this, okay? And if the constant, we have this. If the constant is negative 4 over 5, then we have this as the solution. So you should convince yourself that a differential equation, an ordinary ODE, can have one or more solutions, infinitely many solutions, okay? So, and this is common, okay? You could verify this. You could verify that verify that y is equal to e power x, y equal to 2e power x, and y equal to negative 8 over 3 e to the power x, okay, are solutions to y dash equal to y. So this is your homework. Verify that y equal to e power x, y equal to 2e power x, and these are solutions to this DE. Okay, this homework is given in the notes. Okay, and have you noted this? So think of if you have integral 0 to pi of sine x over x dx, integral 0 to 1 e power negative x squared dx. Can you solve these problems analytically? I don't know. Is there a way you can find this solution with hand or analytically? But a computer can do it. Or we can have numerical approaches to do it. That's why we need to study analytical techniques. And if we can't solve it analytically, then don't you think a computer can be of use to help us to solve it, or we revise analytical approaches and exhaustive search, okay, to find solutions? So these are some of the scenarios where you may have a solution or an NDE that you can't solve analytically and you need methods to do it, okay? So we've looked at this case, question 6, how it becomes a solution to this ODE, okay? And we've realized that sometimes a solution of a DE appears as an implicit function that is implicitly given in this form of equation 7. So equation 7 is called an implicit solution in contrast to the explicit solution that we have in 6. Okay. Example, I've given you this, okay, is an implicit solution of the DE given in 9. Okay. So what you need to know is that the key aspect in the solutions of ODEs is to find all the solutions of a particular differential equation. And this is going to help us to investigate the properties of the solution. Are the solutions eigenvalue problems? By eigenvalue or eigenvectors, you've studied something of this form, right? And you know that eigenvalues and eigenvectors are very fundamental as far as engineering is concerned. For example, a control engineer or an electrical engineer can use eigenvalue problems in stability analysis. If you need to analyze stability of a system, then you may need to know the kind of solutions that you are getting for your problem or your ODE or any problem that you're dealing with, because it can be fundamental in determining the stability of your electric circuit. Okay? If you are a communications or an electronics engineer, and assuming you need to transfer information, okay, or you have a tower or a base station or what you call mast, okay, in my local language you call it omulongoti. I don't know what you call it, but you have a tower and you need maybe to focus your power or information in a particular direction to maximize coverage. Okay, you need a way of doing this, because you may find that you need to supply that side of Teso College, and then you need to supply the side of where the city is. Okay, then you need to supply the side of Hase Resort, and then you need to supply the side that is behind the main building of the university. So you find that you need to maximize coverage in all these directions. But you find in all these directions that I've mentioned, the city side, the Teso College side, and the side behind the university, there is where you have maximum population. And this is where you should focus much of the power, because you need to cover the people efficiently for them to communicate. So how are you going to allocate the power? Because you would be a wasteful engineer if you give them equal shares, because they have different needs. And you and me should agree that the part of the city has majority of the population. And this is where much of the power should be assigned. Okay, so if you know the solution of your ODE or the solutions of your problem or the power problem, then you can, let me say, one of the eigenvalues is 0.8, one is 0.5. Let me write this here to make more sense. So assuming you have your tower, okay? This is your tower. You have your antennas. You have an antenna that is going to face this side, okay? You have one that is facing this side, and you have probably another one in a particular side, assuming this is 3D. So this is soroticity. This is that side that has the orange factory or the Hase Resort side. And this is behind the headquarters of Sun. So you know that you have majority of the population. So more power should be sent here to the city. Okay? So having a solution of your ODE in terms of an eigenvalue problem, you might find that this is 0.8. Okay, then maybe you have this side, let me say, of Teso College. We have more students here. You could have a solution of 0.5, and then here, let me say 0.5 here, 0.3 here, and 0.2 here, because you have a few people here, okay? So this gives a total allocation of 1, okay? And we can see that our power allocation factors are 0.5, 0.3, and 0.2. So this implies that if these were solutions, eigenvalue solutions of your ODE, then you're going to find out that they are going to help you to determine which side you should allocate more power, which is 0.5, because you need to give more factor to the power. Just imagine if you have a constant transmit power. When I use TX, I mean transmission, okay? If you have a total transmit power of maybe negative 30 dBs, you're doing a course in analog electronics, right? So analog electronics, you've looked at decibels, okay? Or more specifically, negative 30 is equal to 10 log 10 px. So this is px as maybe 3 milliwatts. So you have a power of 3 milliwatts, okay? And if you're going to serve sorority city side, you're going to have 0.5 times 3 milliwatts. And I think this is going to be 1.5 milliwatts. And then this other side, you're going to have 0.9 milliwatts. Okay? And this other side, you're going to have 0.6 milliwatts. So you can see that you've efficiently distributed the power, the 3 milliwatts, into the different direction, but depending on which one needs more allocation. And by so doing, you are efficiently utilizing the power as an engineer. Okay? So all this comes with solutions to our numerical problems or ordinary DEs or any problem. Okay? Which you may not specifically be able to solve with analytical skills, but you need the numerical side to help you. Okay, so sometimes what I mean, solutions to ordinary differential equations can have infinitely many solutions, and these are going to help us to determine. And also, as an electronics engineer or telecommunications engineer, it's going to help you to determine the strength of the channel. Okay? It is going to help you to determine the strength of the channel. The channel, I mean free space, which you call the vacuum. You used to study, I think, magnetism in high school. It can be fiber. It can be copper, depending, okay, the medium of transmission. So, and you know that if you're communicating with your towers or your electronic equipment, you want A to communicate with B. Okay? As an electronics engineer, you are sending this through free space. Okay? And you may find that you have several antennas here. Let me do this here. So you have this. Okay? You have this here. So you have a channel that is connecting with this first antenna. Then you have another channel that is connecting to this antenna. Then you have another channel that is connecting to this antenna. So assuming this is Bob, this is Alice, this is Eve. Bob is trying to talk to Olivia. This one is trying to talk to Jack. This one is trying to talk to Eve, is trying to talk to who? To James, okay? So you may find, depending on the conditions, the weather, because you know that when it rains, your signals are not so good. And when again, there is a lot of sunshine, the signals are a bit affected. So maybe you find the channel where Joanne is, there is rain, okay? So, and maybe their channel is a bit weaker. And you find the channel between Jacob and Alice is good. It is a bit stronger. Okay, it is good. There is no rain, there is nothing. So it is clear. You have like a line of sight. Line of sight, I mean, they are communicating properly. Okay, the same thing. So, and you find maybe this one is average. Okay, so if you know that the channel between Jacob and Alice is my win situation, okay, and you already know that this channel is poor, if you know your solution of your ODE or the power ODE, depending on your current, you're going to, it would be wasteful, and if I'm your boss, I would sack you to allocate more power in a weaker channel. I would expect you to allocate more where you're winning than wasting power here on a channel that you know is not working properly. So your manager will tell you, go and try to fix this channel to communicate well. Okay, so, and all this, assuming this is our X, the transmitter, you are transmitting X and you're receiving Y. And this is through a medium, which is our channel. Okay, the medium, which we call the channel. So these coefficients here between the channel here affect the received signal, because you know that sometimes when you're speaking with somebody, this is all electronics. Okay, you're speaking with somebody, sometimes their calls break. And that is because of the quality of the channel. Sometimes it even goes off. So you need to know the performance of your channel. And you may find, if assuming you have 2 people here and 2 people here, then you have a 2x2 matrix. Usually we have a channel matrix with a 2x2. So you're sending 2 and you have HX, okay, and this is X. Then usually at the receiver, we have some kind of noise. So plus the noise, okay, this is a vector. And this is a matrix, a vector, and this is a vector. So you have, this is a 2x2, because you have one person here and another person here. Then this is a 2x2 channel, okay? Then this is a 2x1, and this is a 2x1, okay? So this is 2x1, okay? So if you have this scenario, you've seen that you're sending these information bits from the transmitter, and at the receiver, you have some kind of noise. When I talk about noise, I don't mean your acoustic noise that you make by shouting. I mean electronic circuit noise. You'll do this in the analog course, okay? So all these, if you have your channel, H/2 channel, and it is a matrix maybe with 0.5, this is 1, 1, this is 0.2. So this, if it is an ordinary differential equation, it shows you which channel is actually strong, okay? Probably, I would prefer to use a channel that has this coefficient of 0.5 than a channel that has 0.2. So I will assign more power here. And this, we can get this through singular value decompositions and eigenvalue decompositions. We shall cover this in the numerical class as well. And this is where the statistics comes from, the statistical bits. Okay, because you know that as electronics engineers or electrical engineers, we model systems based on randomness. Okay, you don't know when a person is going to make a call, but you can predict. Okay, so if you can predict, then can't you build models based on differential equations to do this? You could probably. Okay. So that is a preamble of how useful the solutions of numerical methods and differential equations can be useful in your career. Okay. So the principal task of the theory of ODEs is to find all the solutions of a given DE and investigate their properties. Because you can find, as you've seen before, that an ODE has more than one solutions, and these can be eigenvalues of each other or factors of each other. Okay. And you could take an example for each of these functions. Y equal to this is a solution of this. We saw that. And I've told you to verify this. So can you solve this differential equation? dy dt equal to ky at y equal to 0? Yes, we can. We have dy dt equal to ky. Okay, so this is dy over y equal to k dt, integral. So this is ln y equal to k ln, kx plus c. Okay, and this could be written as log to base e y equal to kx plus c, and y can be given as e power kx plus c. So you can see that you can have this solution, okay, explicitly written as this. So, and you could bring this to the left-hand side, whatever you want to do, okay? So that's one way of solving ODEs, but this is a very simple way. And can we look at it in details? Can take a look at this. So a first order differential equation with an initial condition is called an initial value problem. To solve such a problem, we must find the particular solution of the equation which satisfies the given condition, okay? So we have this problem, the initial value problem given there. Can we find its solution? We haven't looked at this, okay. So separable ODEs, I've given an example, and many first order ODEs can be reduced to equation 14. You can see gy y bar equal to fx. I'm going so fast here because you've looked at it in high school, and more conveniently it could be written as equation 15, where you put the terms of x to one side and the terms of y to one side, okay? So we call such a separable equation, okay? So we could take an example. Okay? So we can take this example to solve 9y. Can do it together here. We have a problem that is solve the DE. 9y y dash plus 4x equal to 0. Okay, so this is 9y dy dx equal to negative 4x. Okay, and this is 9y dy equal to negative 4x dx when you take this the other side. So when you integrate and integrate, you'll get 9 over 2y squared equal to negative 4x squared over 2. Okay, and this can be plus a constant c bar. Okay, so if we rearrange this solution, you will agree that x squared over 9 plus y squared over 4 is going to be equal to c. Okay, or simply written as our c is going to be c bar over 18, the constant. This is after algebraic manipulations. Okay, multiply throughout by 2. This will be 18. This will be c. Okay, here you'll have 18. Okay, you could do this here. This is 9y squared plus 4x squared equal to 2 c cap. So if we divide through here, divide by 9, by 9, by 9, we shall have y squared plus 4 over 9 x squared equal to 2 c bar over 9. So if we divide by 4, by 4, by 4, so this will be y squared over 4 plus x squared over 9 as equal to c cap over 18. And this is another constant which we could let to be c. So, and that's why we have this as the solution. Okay, have you copied this? Or you don't need to?
We've copied it.
Okay, great. So, what if we take another example? What if we take another example? We have another example that is x solve the initial value problem x squared plus 1 y dash plus y squared plus 1 equal to 0, given that y0 is 1. Okay, so we can have x squared plus 1 dy dx as equal to negative y squared plus 1. Okay, and then we have dy over 1 plus y squared is going to be equal to dx of 1 plus x squared. So when we take the integrals, integral dy over 1 plus y squared equal to integral of dx over 1 plus x squared, this is going to be tan inverse. This has a negative, right? And this has a negative, right? Okay, so we can have tan y plus tan inverse of x, and this can be equal to an integrating constant c. Okay, so and we can let tan inverse of y to be equal to a and tan inverse of x to be equal to b. So this is going to imply that a plus b is equal to c. So if we introduce tan both sides, this will be tan c. And this is going to give you tan a plus tan b over 1 minus tan a tan b. Okay? And what is this going to give you? This is the same as you having.
Excuse me, sir.
Yes.
Our power is going off soon.
You what?
We have power shortage.
At what time? Hello? Hello? Okay, so this is going to be y plus x over 1 minus x y. Okay? And you're going to find out that when you do substitutions, you'll find out that tan c is going to be 1. When you substitute for x equal to 0 and y equal to 1, tan c will be 1. And you'll find out that the solution to your ODE is y plus x over 1 minus xy equal to 1. Or simply, y equal to 1 minus x over 1 plus x plus x. Okay? And because of that, then we can go to equations that are reducible to separable form. Okay? So we've looked at this. We've looked at this. You can try out equation 17, okay? And then you have a homework here, okay? So you have a homework here. Now we can look at equations that are reducible to separable form. Certain first order DEs are not separable, but can be made separable by a simple change of variables. This holds for equations in the form of 19, where y dash is gy over x, and where g is n given function of y over x. For example, it could be this, it could be this, and in this form, we suggest to set this fraction equal to u, okay? And we can take an example of this, okay? So you have 2x y dash minus y squared plus x squared equal to 0. Okay, so we want to solve this solution. We could start by dividing throughout by x squared, and this is going to yield 2y over x, y dash minus y over x squared plus 1 equal to 0. So if we set y over x to be equal to u, then we shall have y equal to ux, okay? And when you perform a differentiation, you will find out that y dash is the same as you having u plus u dash x, okay? And when you make substitution, you'll have 2u into u plus u dash x minus u squared, okay, plus 1 equal to 0. And this is going to yield, when you do mathematical manipulations, over 1 plus u squared equal to negative dx over x. So when you integrate both sides, you'll find out that you have ln 1 plus u squared equal to negative ln x plus c bar, okay? Or literally, you have 1 plus u squared equal to c over x, okay? And when you make a substitution, you'll find out that you have a solution. Your final solution will be something like, you have x squared plus y squared equal to cx. Or simply, when you carry out completing squares, you'll find out that you have this squared plus y squared. equal to c squared over 4 after completing squares. Okay, so that's one way. I've given you a problem to think of. Then we shall start our exposition tomorrow. Maybe let me do this last example. You can be given to solve solve 2x minus 4y plus 5, and this is y dash plus x minus 2y plus 3 equal to 0. Okay, so you can see that in this case you can have 2 into x minus 2y plus 5. This is y dash plus x minus 2y plus 3 equal to 0. And in this case, you can see that this is common. So you could easily let x minus 2y equal to u. Okay? And this is going to imply that when you take a derivative, you're going to find that y dash is simply a half into 1 minus u dash. Okay? And when you make a substitution, you will see that you have 2u plus 5. Instead of this, you're going to have v dash, and this will be 4v plus 11. Okay? So at the end, you're going to have a long division. You're going to have 2u plus 5 over 4u plus 11, then dv equal to dx. Okay, with the 2 because of the half. So when you carry out a long division, what is going to happen? What's going to happen when you carry out a long division? So you will have something like 2u plus 5. This is 4u plus 11. Okay? So when you divide this by this, you'll get a half. Right? You'll get a half. And this, you'll get 2u. This and this, you'll get 11 over 2. Okay? So this minus, you'll get a 0. This, you'll get a negative a half. And that's why you end up with something like, you'll end up with something like a half minus a half of 4u plus 11. Okay, this long division. And it is going to yield something of 2dx, and this right-hand side will just be simply 1 minus 1 over 4u plus 11 du equal to 2 dx. Okay, so you have this. And when you solve that, you'll find out that you're going to get, when you take the integral of this, you'll find out that you are simply having your v or your u minus a quarter when you integrate ln of 4u plus 11 equal to, so you're going to find out that you have your u minus a quarter ln natural log of 4u plus 11 equal to 2x plus c cap. And when you substitute back for u equal to x minus 2y, you'll find out that your solution will be 4x plus 8y plus ln of 4x minus 8y plus 11 equal to another constant, c. Okay, and this will be the solution. So this marks the end of today's lecture. So from tomorrow's lecture, we shall cover exact differential equations. Then we shall go on to look at integrating factors. And then we shall go on to look at the methods of variation of parameters. Then we shall look at existence and uniqueness of solutions. And then we shall conclude the first order differential equations by looking at an application, particularly in electric circuits. Thank you. Unless you have a question. If you have a question, you can unmute yourself and you ask. I didn't talk about the grading and I didn't talk about the cut. Let me talk about this briefly. You're going to do your first cut. I'll put this here. So, grading. Usually, I give 40% in 2 written tests, each at 10%. So 2 times 10 is 20%. Then I give 10% in written homeworks and 10% in math lab assignments. All these are done in groups of 4-4. Apart from the 2 tests, these are individual. But if you prefer, I can also give a take-home test take-home test. One of the tests can be take-home. I send the exam like at 8 a.m. in the morning, and then you submit your solutions by 7 p.m. in the evening. So if you prefer, we would have one test like this, okay? And one test will be sit in. Or this take home can be optional. 2 tests can be sit in, then I usually give an optional 3rd test. Only register it if you're going to take it. If you register it and you don't take it, you will lose marks. So, and the final exam, this is continuous assessment tests and coursework. Then the final exam is out of 60%. Usually there are 5 to 6 questions. Each has 25 marks. You choose 4. Okay? So that is it. Do you have any questions? If you don't have, thank you. See you tomorrow.